focus that. Okay, so why vectors? Quantities that involve both the magnitude and speed, and then the direction is due north. So anything that involves some kind of like magnitude or some kind of scale and then direction, that's why vectors are really useful. Okay, it gives us more information about how a certain object or how something is moving. Before we kind of jump into the first example, let's come up with some like notational things with vectors, and this would be the first thing I'd start adding into your notes. So there are multiple ways of how to write and represent vectors. We're going to write it in terms of the what's called the I and J components. So if we have a vector spanning from the origin at 0, 0 to point AB, it is represented by vector V, which is equal to A times I plus B times J. The real numbers A and B are called the scalar components of vector V. And then note that A is the horizontal component, B is the vertical component. And then the sum, or AI, or A times I plus B times J, is the linear combination of the vector. And then the last thing that we're going to be doing today is finding the magnitude. And so the magnitude of vector V. Notice the notation here. It's like two absolute value brackets. And then that's how we'll find the magnitude. I'll write that out a couple different times before. We'll see that equation a couple different ways. Okay, but I'd go ahead and add in everything I underlined into your notes. And I'll give you all a few minutes to do that before we move on. One of the things is finding the magnitude. And we're going to also, and this shows up on your map, show that the magnitudes are the exact same. But then we'd also have to show that the directional component is also the same. And there's multiple ways of how we can do that. One way that is probably the most basic is if our vectors are drawn in like our coordinate grid system, is to simply find the slope. Okay, so what we need to do is, and I don't know that I would jot down this entire picture. If you want to, that's fine. We are going to work with these points, but our main task here is just to simply show that vector u is equal to vector v. To do that, like I said, we need to show that the magnitude and the direction are equal. And so basically I'm going to I'll find the magnitude of one of the vectors as well as a way to show the directional component, and I'm going to have you all do the exact same. Now with these vectors, there's a terminal point as well as an initial point. Just like when we draw angles, right? When we were drawing angles, angles have an initial side, that's the side that doesn't move, and then the terminal side, that's the side that does move. So initial point and then terminal point being that end point. And so the first thing that we'll go ahead and work through is showing that the magnitudes are the same. So for the magnitude work, we're going to define, I'll go ahead and do the magnitude of v, and I'll have you all find the magnitude of u. And we're going to use a different form of the equation you all just wrote down before, and that equation is going to be the square root of, basically this comes from the Pythagorean theorem, and I'll show you that here in a second, but the difference of the x coordinates, so x2 minus x1, and all that squared, plus the difference of the y coordinates, y2 minus y1 squared. And really all this is the Pythagorean theorem. Okay, if we had the magnitude of v squared equals the horizontal component squared plus the vertical component squared. Okay, and one way to see that is I have this vector v, which it's a line, right? That's all that it is. It's a line starting from one point, ending at another. Well, if I go ahead and draw a triangle connecting the terminal and initial point, that creates a right triangle. I'm working with right triangles. If I want to find the length of the hypotenuse, a squared plus b squared equals c squared. C squared being the magnitude, a squared being the horizontal components, b squared being the vertical components. Okay? So this method will work even if, as long as we have the initial and terminal point, we can find the magnitude here pretty easily. So let's go ahead and work through this. Typically, it won't matter what we call like x1, y1, and x2, y2. For one thing that we will do, it will matter, and so I'm going to just keep things consistent, where the terminal point we're going to always label as x2, y2, and the initial point will be the x1, y1. So when I plug these things in, x2 is 3, x1 is 0, so it's 3 minus 0 squared, plus y2 being 6 minus y1, which is 0, squared as well. So that's the square root of 3 squared plus 6 squared, which is the square root of 9 plus 36, which is root 45. When we're taking square roots, if it is not a perfect square, you will have to reduce that down. MathXL is always very picky about that. So when I go to find root 45, we need to factor out perfect squares. Some of you are really good at this. This is also something that a lot of you struggle with, and there's lots of ways to do this. What I've always recommended is only look to factor out perfect squares. Don't just think about any random numbers that multiply to 45. Think about numbers that factor into 45 that we can take the square root of and be whole numbers. So a perfect square that divides 45 is 9. So I can factor this to be root 9 and root 5, where root 9 is 3, and root 5 does not have any perfect squares to factor out. So root 45 is equal and simplified to 3 root 5. And that's what we would say the magnitude of vector v is. So I have the magnitude for v. Now let's go ahead and find the directional component. And in this case, when we're working in like our rectangular grid, we can find the direction by just simply finding the slope of that vector. So a reminder about slope, and again, this is review from Alg 1/Alg 2, is that it's y2 minus y1 over x2 minus x1, also known as change in y divided by change in x. So I'm just going to use the same x2, y2, x1, y1. So y2 here is 6 minus y1, which is 0. And then x2 is 3 minus x1, which is also 0. So that's 6 divided by 3, which is 2. So the slope of vector v is 2. All right, so what I'm going to have you all do real quick is find the magnitude and the slope of vector u. I'll zoom in on these points, that way you can see them a little bit clearer. I know it's kind of hard to see up on that screen right now, but just to kind of get some practice with finding magnitude and slope, let's find that with these points here being 0, 3, and -3, -3. Okay, let's go ahead and do that now. Yeah? You can. Absolutely can. It's all the same. Yeah, all the same. That equation for magnitude is derived from the Pythagorean theorem. So, yeah. So, to find the magnitude, again, all the same, be careful if you're plugging things into this formula, there's a lot more negatives with that second vector. And when we add in more negatives, that's really just more opportunities to make mistakes. So when you're doing that x2 minus x1, be careful because the x1 is a negative. So it's 0 minus -3. Now, if you didn't catch it, it's not going to make a huge difference because this ends up being squared. -3 squared and +3 squared are both 9. So it doesn't make a big difference there. Okay? But in the second part, that vertical component, when I take y2 minus y1, if you do not pick up on that it's 3 minus another negative, you end up getting 0. And 0 squared is very different than 6 squared. Okay, so you have to be very careful with the negatives. The more negatives we have, more opportunities we have to make mistakes. Okay, but after adding all that, get the same thing, 3 squared plus 6 squared, so root 45, which is 3 root 5. Then the slope, again, we got lots of negatives. When we have more negatives, it's really easy to make mistakes. So 3 minus -3 is 6. In the denominator, 0 minus -3 is 3. 6 divided by 3 is 2. Since they're the same magnitude and slope, we can say that these vectors are the exact same. And that's it. Okay, so nothing crazy, all algebra, all work you've done before. Just working with it with vectors. Okay, well, we have just a little bit more and then we'll take our break. So 2 more problems. When we come back from our break, it's just like a really easy thing with some of these vectors. But one thing is sketching a vector when we are given the I and j components and then just finding that magnitude. Nothing too hard here. One thing that I just want to point out, and you basically took notes on this before, that with this vector v, the number in front of I, that would be our coefficient for a. So in this case, a is -3, and this is our horizontal component. And then the number in front of j, that's the b value, so b is 4, and that's our vertical component. So when I want to sketch this vector, if we're just given a horizontal and vertical component, we'll let that initial side be at the origin at 0, 0, just to make this a lot more simple. If we wanted to change that initial point and make it a lot more complicated. So we'll put the start point here, and again, I'm going to call this the initial point. And we're going to let that be equal to P1, because eventually it is going to matter what we call point 1 and point 2. And so from that initial point, we're going to go horizontally by -3 units, so left 3, and then vertically by 4 units, so up 4. So left 1, 2, 3, and then up 1, 2, 3, 4 brings us to the terminal point, which is going to be equal to P2. And the vector is just us connecting these dots, but there is an arrow tagged on to that terminal side. And again, that's basically what's showing that directional component here. Okay, and that terminal point is -3, 4. And so the last little bit for us to find the magnitude is to basically do the same thing we did before. Now, one thing that we can do, and an equation you have already written down about finding magnitude, is that when we have the directional components, the magnitude is equal to the horizontal component squared plus the vertical component squared. So we can just use a squared plus b squared. I don't need to do the whole x2s minus x1 and y2s minus y1s. Okay, I can just simply square the values I already have. So this is equal to -3 squared plus 4 squared. So that's 9 plus 16, which is root 25, which is equal to 5. So the magnitude here is just 5. Nothing crazy once again. Main thing, just pointing out where our initial point is, terminal point, and the fact that we're going to call them P1 and P2. Point 2 will always be the terminal point. Okay, one last quick example, and then that's when we'll go ahead and pause and take our 5-minute break. And then, like I said, when we come back, not a whole lot more that we need to get through. But the last thing, before we jump into this break, is if we're given 2 points, taking that information, or taking those points, and writing the vector in terms of its I and j components. So we're going to let v be the vector from the initial point, P1, which is at 3, -1, to the terminal point, P2, being -2, 5. Now, it's really important that, again, the terminal point is this point 2. And so when we go to apply, it's basically just subtraction, but this P2 is our x2, y2, and P1 is x1, y1. So in order for us to write this in terms of its I and j components, vector v is going to be equal to x2 minus x1 times the I plus y2 minus y1 times j. So all we gotta do is just plug these things in, do a little bit of subtraction / addition, and that's it. So x2 is -2 minus x1, which is 3, plus y2, which is 5, minus y1, which is -1, times j. So this is -5i, and then plus 5 minus -1 is 6j. And that's it. Nothing else to that. Okay, well, we'll pause right there. I will round up the time. We'll call it 3:19. So at 3:24, we are back. Moving on, and again, we just have a little bit more left to cover. All right. Before we move on, just a quick note about when we're writing vectors in terms of its I and j components. And I didn't mention this, but I think it's worth us writing this or adding this into our notes. So when representing a vector from an initial point to a terminal point, does the order in which you perform the subtraction make a difference? The answer is yes. When writing a vector from point 1, where we have x1, y1, to point 2, where we have x2, y2, point 2 must be the terminal point. Okay, and the order in the subtractions is important. Okay, so I would just add that in. Otherwise, the direction component of your vector is completely off. It basically just makes it negative. Okay, or if it was negative, then it ends up making it positive. So really important that if we're given 2 points, point 2 needs to be the terminal side of the vector. Okay, and then the rest of this is just saying, notice how it's different from when we find distance. Because of the squaring, the order in which we do the subtraction doesn't make a difference. But when we're writing the vector in terms of I and j, it absolutely matters. And I'm going to be consistent with all my work. Anytime we're working with a vector, I'll call that terminal point point 2, which is x2, y2, and the initial point, point 1, which is x1, y1. And the last thing that we're going to cover are just order of operations with vectors, so adding them, subtracting them, multiplying them, and it should feel natural is kind of the word I've been describing for that. Okay, but I'll give you a sec just to make sure you have this written down. Again, only write down what I have underlined. The rest of it is just kind of extra. But what I have underlined really describes the important piece here. All right. So, adding, subtracting vectors. For a hot second. One sentence right now. All right, so adding, subtracting vectors. If you want to write down the general way to do this, feel free. Again, to me, this feels, the way that we add them together feels natural. So I'm not going to have you write this down unless you feel the need to. But if I'm adding vectors together, basically this is saying add the horizontal components together, then add the vertical components together, and you're done. That's exactly what I would expect to do. If we're subtracting the vectors, subtract the horizontal components, subtract the vertical components. Okay, so to me this feels like exactly what we would expect it to be. So I'm not going to even have y'all write that down again unless you really feel the need. So let's jump straight to the example where I have vector v equal to 5i plus 4j, vector w equal to 6i minus 9j, and we're going to find v plus w and then v minus w. And again, all we're going to do is add the horizontal components together, add the vertical components together, and then subtract them. So v plus w is equal to the horizontal components together, 5 plus 6i, plus 4 minus 9, or 4 minus 9j, which is 11i, and then 4 minus 9 is minus 5j. And that is vector v plus w, all done. Then v minus w, the exact same. We will take the horizontal component of v minus the horizontal component of w. So be careful, the order in which we do the subtraction does matter. So 5 minus 6i plus 4 minus 9j. 4 minus negative 9j. Okay, be careful because that is a negative there. Do the 4 minus negative 9. Like I mentioned earlier, the more negatives we have, more opportunities to make mistakes. 5 minus 6 is negative 1, so that's negative I. And then this is plus 4 minus negative 9 is 13j. And that's vectors v minus w. Now, we're really only doing basics with vectors. We're not going to do anything super complicated. But for those of you that take a math class beyond this class, or even like this shows up in physics, like anybody taking physics and worked with vectors in here already, okay, so some of you are already familiar with this. I do want to provide a visual as to what's happening when I add or subtract vectors. I'm not going to ask you to do that in here. We only have a few days. If we had more time, we'd maybe spend some time with that. But in like physics, vectors are a huge piece of that. If you move to higher level math, vectors get used all the time because of the fact we have that directional component and the scalar component. So just to show this real quick, if I had two vectors and we wanted to add them together, let's say we have vector u and vector v. We position them so that the first vector that we're adding, u, starts at, we'll say, the initial point of u. And then we take the second vector and position it so that the initial point is at the terminal point of the first vector. And then we have that directional component to it. And the resulting vector is just us connecting the original start point to the new end point. Okay, so it's a brand new vector once we add them together. Again, that's not anything you need to know for what we're doing in here, but that visual does kind of show and like what's going on here and how we can add them and how that translates into a brand new vector. When we subtract, I don't love this diagram. To me, there's just too much going on. But we're basically doing the same thing. We're positioning one vector, its initial point, and then we have the terminal point, and the vector we're subtracting, basically we think about this as being v plus negative u as opposed to v minus u. So vector u, if we want to make that negative u, it just changes the direction. So now it's going in the opposite direction. And then we'll take this negative u and position it so that the initial point is at the end of the first vector. And then we have our new endpoint here. And the new vector, again, going from our start point to the new end. Okay, so they almost always work out to be, not almost always, they always work out to be a triangle. But again, nothing that we need to know. Just wanted to provide that context for those of you that might end up seeing more vector stuff here in the near future. So the last thing that I'm going to share with you all is scalar multiplication. So if we take our vector and multiply it by a value, how that works out, once again, it's, to me, it is exactly what we would expect it to be. So if I have vector v and I need to multiply it by k, we multiply each component of the vector by k. So if you want to write this down, feel free. But again, I feel like this is pretty obvious, so I don't need to write this all down. So if I have vector v, and I want to find 6v, all I'm going to do is multiply each part of the vector by 6. 5 times 6 is 30. 4 times 6 is 24. That's it. To me, that's what I would expect to do. B, same idea, but now I'm going to multiply everything by -3. So -3 times vector v makes this -15i minus 12j. No, nothing to simplify. Yeah. All right, and then the last thing is if we have multiple operations with multiple vectors, mainly just a reminder that order of operations matter. Okay, if I have a vector v and a vector w, and we want to find 4v minus 2w, we have to do the multiplication first. Order of operations still matters. So before I even do the subtraction, I'm going to find 4v and 2w, and then I'll do the subtraction. So 4v, where I take every component in the v vector and multiply it by 4 to get 20i plus 16j. And 2w is 12i minus 18j. And then 4v minus 2w. So now we'll just take these components and subtract them. So this would be 20 minus 12. That's our new I component. Plus 16 minus negative 18j. And now this just needs simplified, which is 8i. And then 16 minus negative 18, so we're really adding, that'd be 20, 34. 34j is 4v minus 2w. All right, friends, that is it for today. The Math Excel covering this content. You'll be able to work through most of the Math Excel, not everything yet, but you can at least get a head start on it. Remember